In this paper, we propose the Volumetric Flying Object Detector, or VOFOD, a new algorithm for LiDAR-based detection and relative localization of flying objects on board UAVs. It provides accurate positions of other UAVs in the environment without requiring any markers, which enables also detection of non-cooperating targets, such as UAVs intruding in a restricted airspace. An observer UAV carries a 3D LiDAR capable of sampling points corresponding to the target UAV when it is within the sensor's field of view and range. However, in a typical deployment, the LiDAR will also sample points of the ground or of background objects. The main goal of the VOFOD algorithm is to discriminate between points corresponding to flying objects and to the background. The first step is separating the points into clusters using the Euclidean clustering algorithm based on a selected threshold D cluster. Let us denote these clusters A, B, and C. Now, each cluster is classified as either background, a flying object, or unknown, based on an occupancy map of the environment. The map is represented as a grid of voxels, with each voxel classified as occupied, free, or uncertain, and these values are dynamically updated during runtime. For each point within a cluster, its vicinity within a distance to close is checked, and if it contains an occupied voxel, the whole cluster is categorized as background. In this case, the first checked point already has an occupied voxel in its vicinity, so all points within cluster A are classified as a background object. No points within cluster B are close to any occupied voxels. However, this cluster cannot be reliably classified as background yet because the area of the environment where the object is connected to the ground was not observed yet. To determine this, the algorithm checks whether the cluster is completely surrounded by free voxels. This is done by performing a depth-first search in the voxel map using free voxels as boundaries. The search is terminated when an occupied voxel is reached, or when all connected uncertain voxels are searched. In this case, a path of uncertain voxels potentially connecting the object to an occupied voxel is found, so cluster B is classified as unknown. Finally, because no points within cluster C are close to an occupied voxel, and the depth-first search terminates without reaching ground for every point from the cluster, it is classified as a flying object. After the cluster classification, the final step is updating the occupancy map. Free space is updated by casting the LiDAR's rays. Points, classified as background objects, are used to update the corresponding voxels as occupied. This process is repeated for each new LiDAR scan. Output of the detector is processed by a point cloud tracking algorithm that relies on a Kalman filter to track the movement of targets in consecutive LiDAR scans, to estimate their states, and to filter out sporadic false positives and negatives. The VOFOD algorithm is already deployed to facilitate UAV detection and relative localization within multi-robotic teams in applications such as cooperative navigation or distributed exploration, and also for the non-cooperative task of intruder UAV interception as part of the Eagle 1 project. It achieves an almost 100% detection recall and a 20-centimeter accuracy at 20-meter range with only 20 millisecond delay. These results are crucial in facilitating autonomous aerial interception of fast-flying UAVs. Thank you for watching. For more information, please visit our website.